Happy Monday. We are in memory organization part or memory hierarchy and cache design. Very important topic in computer architecture. So let's see what we had before and what we're going to do this week. So what normally we started last week was about memory hierarchy, and is this memory hierarchy or memory organization or cache design is actually very good engineering example how you can design something to improve, for example, performance or something. It's very practical. Maybe you don't design a cache in your carrier, but this is going to give you lots of ideas for other purposes. So we started talking about memory and processor last week, and we mentioned that memory is always slower and even get slower because the size improving and CPU get faster and faster. So how we fill this gap, that was the idea. The bad news is that if you make the memory fast, like technology is too expensive to make faster memories and also make lots of heat. So that's something that we need to consider. If you want to have higher performance memory, we need to consider lots of budget and money and cooling. But good news is that there is some advantage that coming from or some privilege that coming from good programming. If the programmer write a structured code or program, so it means it's modular, it's kind of not using goto a lot and use iteration or loops or selections, and kind of write the code that the flow is predictable. The flow of code is predictable. In that case, we call that type of programming a structured programming. So if a program is structured, it has some privilege in terms of the way that we can take advantage for improving performance, and that's coming from locality. So we talked about temporal locality and spatial locality. We said if we use actually something, a part of the memory, you will likely use it again. So this is a temporal locality, so because it's in a time. And also we have a spatial locality that focus in surrounding that area. If you access something, you will likely access nearby that area as well. So it's better to be closer to the CPU. So these two privilege let us to kind of design cache that actually have higher performance or high hit ratio or low miss ratio. That's what we're going to talk also today, to see what other methods we can use to bring the penalty of missing lower and lower as much as we can. So what we also talked last time was how we can take advantage of this privilege that locality give us. it was a couple of methods that we're going to talk also today, some of them. And like, for example, we can use cache. Cache is something fast, but not a very big cache, a small cache close to the CPU. And we divide it by blocks or lines. In cache, we call them lines. In memory, we call them blocks. And size of line or size of block is much better than, much bigger than a word, like maybe 16 words, 4 words. And that let us, when we are bringing something, we also bring surrounding that area as well to maybe we want them later. If the program is structured, we might need them. Like, for example, is an array, for example. And also, we can use some replacement methods because the cache is smaller, memory is bigger. It means so many blocks in memory should overwrite in one line of cache or multiple set of lines in the cache. So which one we replace? So even we can have some algorithm for replacement. Like, for example, say, okay, let's do least recently used. When you want to do replacement, do the one that is not used recently. Because of locality, again, temporal locality, same rules. So this gives us lots of actually privilege to use that to improve performance. So that was the cache. So we can use cache, and we can use blocks or lines. Also, we can do something that is called mapping. We're going to start it today. So it means, because we need to do mapping. Again, the memory is big, the cache is small. How we know which element of the memory go to which element of the cache? This is called mapping. We have different type of mapping, like direct mapping. So the mathematical method of mapping is with mode or modulo arithmetics. So you are working with reminders. So in modulo arithmetic, you are working with reminders. So when you divide something by something over something, that's you are dealing with reminder. The mode is coming from that modulo arithmetic, working with reminders. So it means, for example, you have, I don't know, 100 elements or 100 blocks in memory, and you just have 4 block in the cache or 4 lines in the cache. So how you know, for example, block number 20 goes in which element? You just need to divide, find actually reminder of 100. The number, for example, was 20, and you just need to find reminder of 20 over 4, because it's 4 elements, and you can find what is the reminder and put it in that. I'm going to have some example to show you what's happening exactly. This is mapping. That mapping has actually increased hit ratio. We're going to see why. That's another one. What else we can do? We can play with the cache size. We can play with the cache size. We can make the cache bigger or smaller. If make it bigger, the probability of when we are accessing that and find the elements is higher. So hit ratio going higher. But at the same time, when it's bigger, get it slower. Anything big is slow. Anything is small is fast. This is the principle, it's the rule. And so we can play with the cache size. We can use cache size. Bigger cache, of course, is slow. We need to find exact size. This is all method that we can exploit locality, take advantage of locality. What else we can do to use locality? We can find some replacement policy. When you want to do replacement, as I mentioned, you can use some algorithms, like, for example, use FIFO, first in, first out, or least recently used, for example. The one that is not used recently, we can take that out and replace it with something else. Another method that we can use to just take advantage of locality is to have multiple layer of cache, not just one cache. We can have 3 layers of cache, layer 1, layer 2, layer 3, and make a pyramid for the, when we increase these layers, we are kind of increasing hit ratio, the possibility of hit. We're going to see that in examples. So this is what we're going to learn in this chapter of the book, or in this week. It is the chapter 5 of the book that we are teaching. And cache design is the main part. I want you guys learn how to design a cache till end of this week. We're going to have lots of examples. Design of cache means finding, for example, which one, based on your information, which size cache you can use, which method of mapping you can use. We have different method of mapping, like direct map is one of them, a set associative, or fully set associative, or n-way set associative. That's all method of mapping that we're going to see advantage of each one. That's called cache design. But before going to the cache, we need to see, because the lowest level of memory is hard drive, or secondary memory, or storage. So that's a place that everything is there. Whatever you have in your computer is in your hard drive, is in your secondary memory. So we need to know how that works a little bit. Also, second layer after hard drive is a dynamic memory, or main memory. We also need to know about that, and something coming up that's called bandwidth. So when you are transferring information, because I mentioned when you want to bring something to the cache, it's better to bring surrounding too. So you want 1 word, but will bring 4 words, for example. So you need to have capability or ability to bring them fast. How we can do them fast? With increasing bandwidth. Bandwidth is like designing the bus in your motherboard. So bus is the place that we have address bus, we have data bus. We want to see how we design that. Because in caching, as I mentioned, you need to bring lots of information. Every second, every millisecond, you need to bring lots of them, and it's always active. So that's something that we want to talk now. But before that, let's do this eye clicker to see what you are thinking about that. I'm going to go to open this eye clicker and start clock. So you start reading that, I start this, I start, yes. Okay, so I'm asking, we want to transfer a large amount of data from memory to processor. Yeah, we want a large amount of data. Which change would most likely improve performance? Increase the width of the data bus, decrease the clock frequency, and increase the memory latency. So memory latency is the time that takes to go to the memory and get the first data back. So that's called memory latency. And reduce the cache size. So which one you think is the best way to improve performance when you want to bring lots of data in? Let's see the result. Yeah, most of you guys selected A, and that's actually correct. So the best way is to, because you want to bring lots of data into, copy into cache. So it's better to have a wider data bus so you can transfer them like a parallel at the same time. So yeah, that's correct. Let I close this. So yes, the answer is A. But why? The reason is here. Memory organization types. We have different type of memory organization. We have one word wide memory organization. We have multiple word wide. We call it wider memory organization, and interleaved memory organization. So we're going to see them in example as well, but let's define them first. In one word, that is the simplest one, memory return just one word per access. So, so in each moment, we just can transfer one word. So lowest bandwidth, but simple to design. That's the advantage of that. The second one is you use like the memory that you can, is like a multiple chip in the memory is accessible at the same time. You can, the multiple memory chips use in parallel. So the memory, when you want to read something at the same time, you can read, for example, 4 words instead of 1 word. That's called wider memory or multiple word wide memory organization. So at the same time, you can use read multiple word, and it's harder for design, but very higher bandwidth. You can bring more information faster to the cache. In this case, you need to have actually bigger bus, wider bus. You need to have wider cache. And at the end that you want to work with processor, if the processor is working by words, you need to have some multiplexer to choose which one get accessed by processor. So at the end, you need a multiplexer. That is the wider memory organization. The more complex one is interleaved memory organization. In interleaved memory organization, your memory designed very specific way that has multiple banks. Most of memories can be designed like that. It's like the instruction, like register file. Do you remember when I said the register file, it has like a 2-port reading? So it's something like that. Similar to that, you can design for memory at the same time. The rest are one word. The bus is one word. The cache is one word. The processor using those words. But when you want to access to the memory, when you get the address to the memory, it can access multiple banks and at the same time read, like in this case, 4 words, but sending them one by one. Finding them is like a parallel because finding is slow as well. Finding one word in a big memory is so hard, and that takes maximum time. But transferring also is important. So let's see how we can deal with the time. Imagine we are dividing timing to 3 pieces. So this timing can be like a miss penalty, or if it's for the first one, you can even call it a latency. But imagine to access one word, we need one little time for sending the address, send address. We need some time for access the memory, access memory, and we need a little time for return data. Okay, so we need some time for sending address and then access the data, finding the data in the memory. If the memory is big, it's so time consuming to just find data. And when we found it, we need to return that back. This is like if you are in a cache and the data wasn't in a cache, you need to do this search. Is the time that you need to find in a lower memory. And imagine that the lower cache is just memory. Okay, so we need this time. And in this case, we want to, and the size of the line or size of the block is, we need to know this as well. Size of the block size is 4 words. We also know the size of the block is 4 words. So in each cycle, we can do one of these. In each cycle, we can do one of these. So, I mean, we need to do this one after each other. So for 4 words, how much time we need to transfer these 4 words? It's going to be, this is for word 1, this is for word 2, this is for word 3, and so forth. If this is in overall, for example, 20, like microsecond or nanosecond, whatever, you need to multiply them by 4. So this is for when you are using one word wide. Any question about this one? Because for each one, you need to send address separately, you need to access the memory separately, and you need to return the data individually. And first done, second, third, fourth, and like that. That's why we are adding all of these latencies or all of these times together. What about for wider memory? Let I erase this. For wider memory, what we need to do, we are sending one address, but at the same time, we can get, so we need some time for, of course, sending the address. We need some time to access memory, send address, and then we need some time to return data. But this can be done parallel. At the same time, when you send address, you can access 4 at the same time and return them back at the same time. So this is going to be very shorter. So 4 times faster than the first one, because everything happening in parallel. Any question about this? But imagine we are doing interleaved organization, interleaved memory organization. In this case, we need sending address for the first one. We are, however, this can happen for all of them. You are sending address and access data, send address, access data. But when you want to return them back, you need to do one by one because the bus is just one word. So you need to do one for this, another for this, another for this, another for this, if you consider this like that. So this is time for return data. So the overall, you need to add send data one time, address access to data one time, but return address multiplied by 4 if it's for banks. So this is how interleaved memory works. Without making complex, without making a wider cache or wider bus, still we get amazing performance because the return data time is very faster. The most of the time wasting for accessing data. And you are kind of helping in that case and improving access data. Make that faster. Okay, any question? Let's go example to see how these work in terms of finding bandwidth. First of all, we need to see what is bandwidth. Bandwidth is the number of bytes transfer per cycle. The number of bytes transfer per cycle. If we increase this, is better. It's better to transfer. It's faster to transfer more bytes per cycle. So we have, let's do for this example. So we have example, we are assuming we are bringing forward blocks. The blocks are forwards. The blocks, as I mentioned, block is the unit of transferring data. In memory, it's called block. But in the cache, we have lines, but same size as blocks. Sometimes we call them even blocks, but most of the time lines. Lines in the cache and blocks in memory. Anyway, we have the size of these blocks are 4 words. But the bus is 1 word. Here bus is 1 word. Here is 4 words. However, we have different bus. The main bus is this one, 4 words. And here is again 1 word. The bus, the size of the bus, okay? So we have this information. We know that sending address takes 1 cycle, access memory 15 cycle. As you can see, 15 cycles to access memory. However, it's based on the size, of course, and 1 cycle to return data. Let's do it for each of these cases to see what is the bandwidth. First of all, to find bandwidth, we need to find how much data we are transferring. Bandwidth, we are transferring 4 words. 4 words. Each word is 4 bytes, so it's 16 bytes. 16 bytes over access time. We can compute access time based on previous slide. So yeah, if you want to find access time for one word wide, it's gonna be 16 over, if you consider access time is sending data 1 cycle, 15 cycle for access memory, and 1 for return is gonna be 17. So this is bandwidth. Is less than 1. That's a bandwidth. Let's do for, oh, is that correct? Yeah, I think so. Yeah, access time is this. We are having 4 bytes 4 words, and each word is 4 bytes. So this is number of um, number of bytes transfer per clock. Oh, oh no, I made mistake. 4 word. Oh no, there is another 4 here because 4 word, each word is 4 bytes. So yeah, it has another 4 for when we are using 1. So we have another 4 here. So I said, yeah, it's right. So this has another 4 here. 4 multiplied by this. Okay, if we use, because why we have 4, because we need to find bytes. We need to find bytes. We are sending 4 words, and each word is 4 bytes too, you know. That's why it's going to be 4. Is that correct? Because for each one we need, for each one we are, for each one we need this time to access. So we need 4 of that. So the bandwidth is 4 bytes. So yeah, that's correct. That's correct. Why is correct? Because here we're going to have it divided by 4. In this case, if we have 4 word wide memory, we can access all of them at the same time. So miss penalty still is the same. Miss penalty is 17, 1 for sending data, 15 for address, and 1 for return. And but the bandwidth is going to, instead of having 4 of these, we have just 4 multiplied by 4, 16. So we're going to have something like 0.94 byte per cycle. That's a byte. It's not word anymore. One of these 4 is because of changing to byte. That's a problem that's happening. What about using interleave? In interleave, the only thing is this miss penalty. This miss penalty, instead of having 17 that coming from this, we're going to have those return 1, like returning data. Instead of having 1, it's going to be 4. So the overall going to be 15, 16 plus 4, 20. So this 20 coming from that. So we had this 20 coming from send address plus 1 send address, 1 access memory, plus 4 return data. So it's going to be 20. So the 20, this is still 16. This is not changing. The bytes that we are transferring is the same. The byte that transferring is still the same, but the value that is changing is this this access time. This access time based on different method of bus. This is also called bus design. You can design the bus like that. This is before caching. We are still not dealing with the cache. We want to see how we can improve the bus to can bring more information faster to the cache. Any question about this? Okay, the complex one is how we compute this 20 that I mentioned with that picture last slide. So it's coming from 1 sending address because it's just send address 1. and then because it's the banks, 4 banks, you can access the memory at the same time, just one access, but you can return 4 words. But when you want to return them back, you need 4 return addresses to add them together. Okay, so that's 20 coming from that. So this is bus design or computing bandwidth for computer. This is actually a good example for that. So the key idea is to bandwidth depends on how data delivered, not just block size, how is delivered, how you're designing the bus. And wide memory, wider memory showing higher bandwidth. And interleaving actually help that a lot. That's a technology, but it needs lots of overhead. If you want to have an interleaved memory, you need to, it's complex. And that complexity is kind of overhead at the same time. But in this class, we're going to learn how we can take advantage of locality. If you have proper locality, so we need to kind of feed this locality, feed this cache properly as well, because it's not just cache and CPU. Under the cache, you have a slow memory, and slower than that is a hard drive that is very, very slow. It has lots of overhead to access one data. In a hard drive, you need to, it's a mechanical thing. The head needs to move. You need to rotate. You need to find the sector. You need to transfer sector. You need the control part. You're going to see them as well today. Lots of stuff happening in a hard drive that makes it slow. Without caching, this system going to be very, very slow. Even any improvement in CPU is not usable without managing a proper and designing a proper memory hierarchy. So yeah, let's talk a little bit about hard drive as well before going to the cache. First, what is sector? The sector in secondary memory or storage is the smallest unit of storage called sector. As you can see in this picture, this is the sectors. It depends the number of disks that you have. You can read these sectors at the same time. And you have a cylinder, and you have tracks. And so inside the sector, you have some information. Imagine sector is like this. In this sector, you have ID, you have data, you have some error codes, like we call them ECC, error correction code. Some of them you learn in digital logic. To find errors, to correct them, like parity error, CRC, and a different method of finding errors and correction. And also you need some gap for synchronizations and aligning with read and write or doing timing. This is for synchronization. So you have lots of other overhead in the sector when you want to use hard drive. Hard drive is, you can have big hard drive, is a mechanical thing, it has lots of overhead, it's very fragile, it can destroy your information. If you just drop it on the floor, it's gonna lose all the information or destroy lots of information there. And yeah, but it's cheap and it's huge. Your information, they are all there. In computer, whatever you have is stored here. If you have other level of memory, they are just copy of this. You just duplicate them. You bring part of that in a memory and then in a cache and in the CPU. They're just repeat of each other. They are just duplication of each other. However, they need synchronization. If you change something, this chain need to go to down, especially when you turn off your computer. Everything need to go back to hard drive. So this is the structure of sector, and sector is the smallest unit of storage. And what's happening when you access a sector? When we access a sector, we normally need to do these steps. We have some queuing delay, because most of the time you just have one hard drive, and many processes in the operating system or threads in the operating system accessing to this. You need to wait a little bit. There is a queue for that. This is like an input and output device. They have some queue that you need to wait to be your turn to use it. So if you have some waiting, if other requests are already being processed, we need to wait for them. We have some seek time. Seek time means moving head. There is a head moving like here, and this is turning too. We are moving to find a track that the data is there. So that's called seeking time, moving the right read and write head of the hard drive to the correct track. And when we found track, we need to actually wait to data comes. Data takes one turn based on the speed, and we need to find the average. In average is half of full turn. Half of full turn we need to wait in average to reach this rotation latency. And then after finding that, we need some translation, data translation time for reading or writing data. And also we need a controller too. Controller also is a digital logic, and that also adds some delay. So we need to add them all to find one sector. So it's lots of time. It's very, very slow. So let's do example. Any question about this? Let's do example. Imagine we have a hard drive, and it has the sector size is 520, and the rotation speed is 15,000 rotate per minute. We need to change it to second, of course. We have an average seek time 4 millisecond, and transfer rate is 100 megabit per second, and controller overhead is 0.2 millisecond. We need to change everything to millisecond. And disk is idle, no queuing delay. The queuing delay is 0. If we find to and if you want to find the disk access time, you need to add all of these delays together. But you need to make the units similar. So we consider all nano milliseconds. So for seek time, to move head, seek time is already given, milliseconds, so it's given. For finding rotation time, so the rotation time is per minute. If you want to change it to second, we need to divide 60 by that. It's going to be 4. And to find the average, because rotation latency is the average, we need to divide it by 2. So it's going to be 2 milliseconds, sorry. And then transfer time given for 100 megabit per second. If we want to find it for 520 bytes, we need to divide it by 100 megabit per second. That is 10 power 6 second, a bit per second. Oh, it's going to be byte in this case. And when we divide it, it's going to be 0.005 like we have 1, 2 here too, but we just remove the rest, truncated the rest. And the rest is just adding them together. That's a total time, 6.2 milliseconds. It's like 1,000 times slower than dynamic memory. And the memory is also, dynamic memory is like 100 times or 1,000 times slower than cache. So without this, imagine how much processor need to wait. If processor working in nanosecond, for example, need to wait a lot to just data get ready for just write back or read from or write in a store in memory. Any question about this formula? Finding average weight, finding rotation latency. So how we found this? You need to see how much you are waiting to sector be ready. So we need to move the head, and this is all given. So rotation speed is also given, but we need to change the unit. That's not very complex. Okay, that's something that we need to know before starting cache. Last time we already talked about access, average memory access time. We said if we have hit ratio, average memory access time is hit time. Hit time is to check the cache, and data is there, we take it. If it's not there, miss happening. We have a rate of miss, and we have a miss penalty. Miss penalty means the time to go to the lower level to find the data and return them back. So in this case, we need to see how we can improve this. The idea that we have this topic is to how we can improve this average memory access time. So the example, we had that last class. So to improve that, let's see how we can improve hit time. How we can improve hit time, we can actually have how we can improve hit time. Hit time is the time to access cache. If we make cache smaller, the hit time is better. That's one way. We need to make cache smaller. But at the same time, when we make cache smaller, miss ratio going up. So that's why multi-layer cache is always help. So this hit time, maybe we don't play with hit time that much right now. What about miss penalty? How we can improve miss penalty? Miss penalty relate to memory, related to hard drive, and we can use, for example, interleaving bus design to improve miss penalty. So that's also we learned. But today, actually today is done, but after this, we want to see how we can fix or decrease miss rate. Miss rate is something that we're going to talk. And tomorrow, Wednesday, we're going to see how we can reduce miss ratio with designing cache. Designing cache means how we map memory to the cache. We have different ways to talk, and we can see how we can improve that. We can talk about that next class. Any questions? This is also called mapping or cache design. That is the important part of this week.